class. Um, Once you log in, you can post your registration on the chat. Uh, so that will be your attendance. Now, I think we looked, I think the last two lessons we were looking at fields. That was our interest. And actually, we were more interested in the Galois fields, which are the finite fields. And you saw how we used it to create very powerful error correcting codes. Uh, we say powerful because you remember most of the other codes we were dealing with before, they could detect two errors and correct one error. But with BCH codes, you're able to design them and decide that you can change the structure of the code according to how many errors you want to be able to correct. That is why BCH codes are very, very powerful. Yeah. So we looked at the case. I think I'm just trying to recap what we did. We looked at the case where you are you're trying to correct one uh, a single error correcting code, BCH code, and we found actually the difference is whatever number of errors you want to correct. The main difference is the number of um, minimal polynomials which you are going to use. Yeah, I think that is one of what we took from that, and I hope everybody got it. Um, the number of polynomials which you are going to use, because we try to get the LCM of the minimal polynomials of um, the terms. I mean, of the what do you call it? Of the field elements. Yeah, and the minimum polynomials will depend on how many errors you want to correct. Yeah, I think so. I hope nobody has a problem with that. And we found like the case where you want to correct with a bit, single bit error correcting BCH codes because we are doing here. These are binary codes. Remember, we have BCH codes, binary BCH code, and non-binary. And actually, what we are going to look at next is actually the non-binary BCH codes. So with the binary BCH codes, we saw that all you need to do is calculate, look for the LCM to get the generator polynomial. So that's what we are looking for. We look for the LCM uh, of these minimal polynomials up to phi 2t. Yeah, and we found, of course, 2t will depend on what is t. So in the case of a single bit error correcting code, we are looking for the minimal polynomial of phi 1t, I mean phi 1x and phi 2x because t is equal to 1. So you have only two minimal polynomials. And we found, of course, the minimal polynomials will depend again on, they also depend on whether you're dealing with 16 with 4-bit messages. Yeah, we saw the case of 4-bit messages here and the case of 3-bit messages. Yeah, the 3-bit message is what we looked for at before. With that, I think I had that table before. This one. It also depends on whether you're dealing with 3-bit messages or the 4-bit messages. Because you can see the minimal polynomials. In this case, we have 2 minimal polynomials. Yeah. Because the minimal polynomials of this also happen to be, there are 2. One of them happens also to be the the generator polynomial. Yeah. We are finding that the minimal polynomials of some of these uh, elements. Because ideally, we are trying to look for the minimal polynomials of each element of the field. Yeah. But we find that minimal polynomials share, the elements of the field share minimal polynomials with its conjugates. Yeah. In this case, what you're calling the conjugates are where you keep on um, uh, squaring the. For example, I think the easier example to give is where you have got lambda to the power of 1. When you square it, you get lambda to 2. When you square this lambda to the power of 2, you get lambda to the power of 4. And of course, the next one will be lambda to the power of 8. Yeah. But I think in this case, we don't have lambda to the power of 8, where you have got only where you have got the 3-bit messages. This is what it means. You have got the 3-bit messages, then you don't have lambda to be. You don't have lambda. Where you have got the 3-bit fields, you don't have that lambda to the 8. So you're only dealing with up to lambda to the 4. So for each of them, you have to go to the maximum. Uh, Up to the maximum after you square. So there is no lambda to the 8. But of course, when you're dealing with this, then you're going to have lambda to the 8, as we have seen. Now we have lambda to the power of 8. The next one would be lambda to the power of 16. But for this field, we don't have lambda to the power of 16 because it ends at lambda to the power of 14. Yeah. Or alpha to the power of 14, lambda, whichever we use. And the same thing, if you went to lambda to the 5, you'd find after 16, you'll be dealing with 32. But again, there's no lambda to 32 with 5. With the 5-bit field elements. Yeah. Because these are the field elements. These are the 4-bit field elements. With the 5-bit field elements. So always remember, I think that is an important concept. You have to keep on raising or squaring the powers for each of them. So if you're starting with lambda, then of course you go to the lambda to 2. Then you find you have lambda, then you have lambda to the 2 to the power of 2. So you don't have lambda to the power of 3. So you have to consider lambda to the power of 3. So that's another element. And therefore look at lambda to the power of 3. Then its conjugate, which is square, lambda to the power of 4. Yeah. So you have to consider, like in this case, where you have you have lambda, then you have lambda to the power of 2, then its conjugate lambda to the power of 4. If you power this, lambda to the power of it is not one of the elements. So what are you missing? You're missing lambda to the power of 3. I think that is only what we are missing. Is then we have its conjugate, lambda, the square of this, lambda to the 6. Then Uh, that I think here we expect, oh, these are the 4 bits. We expect to go up to lambda to the power of 14. So you have lambda to the 6, lambda to the 12, and now we try to see what is missing. Of course, 5 is still missing, so you need, these are the conjugates of this. We might find that we need more as we try to get all the field elements. So the next one is lambda to the 5. Lambda to the 5 is not there. You have now up to 4 lambda to the 5, and that will give us the other conjugate is lambda to the 10. Now to get the other lambdas is interesting because lambdas we have how many powers of lambda do we have? We have the lambda to the power of 1, lambda to the power of 2, lambda to the power of 3, lambda to the power of 4, lambda to the power of 5, lambda to the power of 6. We still need lambda to the power of 7. You can see we are choosing the ones which are prime. For 7, we have power of 14. And I think that's normally the maximum. So we have to see what we are missing. So we have lambda to the power of 7, lambda to the power of, oh, sorry. I'm looking at the wrong case. This is the case of the 3-bit field element. I'm looking, sorry about that. I'm looking, oh, maybe we stick to the case of, now for this case, of course, it's straightforward because after that, you have lambda to the 3 only. So you have lambda to the 3. Yes. So you have lambda to the 3, and then lambda to the 5. You have lambda to the 3, lambda to the 6, and then lambda. Now here, the lambda, you're getting lambda to the 5 from this actually. That's why lambda to the 5 is coming here. Because you can get lambda to the 5, in this case, from lambda to the 7 by just getting this lambda to the power of 12, which is lambda to the power of 7, into lambda to the power of 5. So lambda to the power of 12 is the same as lambda to the power of 5. That's why to get this minimum polynomial, you see we are multiplying lambda to the 6. We are multiplying x plus lambda to the 6 into x plus lambda to the 5 into x plus lambda to the 3. Yeah. You notice that some of it will be a bit difficult to just recognize at once, especially where you are not given, because in some cases you could be given the minimal polynomials, but some cases you're expected to work out the minimal polynomials. So it's good to understand how you work out the minimal polynomials. So the minimal polynomials will simply be that. These are the 2 minimal polynomials. And as I said, these minimal polynomials turns out to be actually, for this, turns out to be actually the prime polynomial with which you use to generate these field elements. Is this one, yeah? In this case, it happens also to be the what do you call it? The prime polynomial, which you have used to generate the field elements. So does anybody have problem with this? I repeated it because I knew it can be a bit confusing, especially how you generate the minimal polynomials if you're not given the minimal polynomials. If you're given, is straightforward. If you're not given, you're expected to work them out like we did with these examples. We work them out. And of course, what is tricky is to get the minimum polynomials, you need to get the conjugates. We call them the conjugates, which means the ones which are just uh, powers. I'm trying to get which is the correct word of calling them. But if you have five, you have this. I'm looking for a general term. Yeah. And if you have to the power of 4, you power it. I mean, you square it, you get to be 8. Because they're simply not powers of 2. So, does anybody have an issue with this? Before we go to how you decode this. I think later maybe you can have also a physical class where you can do an example or two, maybe later, and by that time you have read, and if there are any doubts, of course, I mean they'll be cleared during the class. Now, I think I'm not sure which week we are in, but I believe we are in the 7th week, if I'm not wrong. Can somebody tell me which week is this? Sometimes I lose track of weeks. Is it a 5th week, 6th week? Now we are in week 8. Therefore, we are not doing so well. I think we have to do our midterm exam next week. We should have done it, I think, in 7th week. But we didn't do it. I believe you have done the others. For the other, I think I missed that midterm exam period. So we are going to do a cut next week. Is that okay?
Can we do it the week after?
The week after?
Yes.
It will not be too close to the exams.
It will be okay.
It will be okay.
Yes.
Okay. I will give it the week after, based on your request, because we are supposed to to do it around the midterm. But I think I missed the timetable because sometimes the department produces a timetable for that. But I think I missed it. So, but anyway, we can do it the week after. That will be okay with me. Now, let's look at, before we get to RS codes, we are going to look at methods of decoding RS codes, how you do it, RS code, and again we are going to look at the case of the binary code. I put it after RS code. BCH decoding. I put it together with, because this BCH coding, it works both with binary and non-binary. So we are going to look at the method for, because actually RS codes are BCH codes. They're just non-binary BCH codes. Yeah. So we are going to look at the case of the binary. Yeah. And as we said, these codes are very flexible when it comes to the number of errors they can correct and detect, and therefore its decoding is slightly more complicated than just one second. A bit more complicated, slightly more complicated than the syndrome decoding. for, let's say, the codes we did, the systematic linear block code we used. And maybe let me just describe it more. Maybe systematic linear block code, or maybe Hamming code. Let's call it Hamming code. Yeah, because Hamming code corrects only one error. Why I'm very particular about how I use terminology is because even BCH codes, you can have a single bit error correcting BCH code, which is similar to the Hamming code. And remember, BCH codes, they are a class of cyclic codes. And cyclic codes are a class of linear codes. So that's why I'm very careful to when I'm distinguishing the codes we are doing, the BCH codes. Because even BCH codes are linear codes and they're also cyclic. Yeah, but they're cyclic. Yeah. So a BCH decoder, of course, what we'll do is to be trying to identify the position and magnitude. We are saying position is which bit is in error, and the magnitude, whether it is 0 or 1, up to t errors, and to correct them. So we are going to use the syndrome method, syndrome calculation, and of course, a BCH code has 2T syndromes that only depend on errors. Yeah. And the syndrome can be calculated by substituting 2T roots of the general polynomial gx into Rx and finding the error locations. This involves solving simultaneous equations with T unknowns. There are algorithms available for this purpose. This one, I thought, let me talk about it. We won't get into a lot of calculation of BCH decoding, but we thought it's good that we have an idea of how BCH codes are decoded, especially the fact that their syndrome decoding involves solving simultaneous equation with T unknowns. Actually, that's the key thing. Because in the other case, when you're correcting only one error, it was easy just to use the syndrome. Yeah. And even with the single bit BCH error correcting code, it will be easy to do the error correction. Yeah. It becomes a bit tricky when you have got more than one error. Yeah, when T is not equal to 1. So again, we are going to use some of this, and that's why I say I just want to talk about it here. I not even test you through this. Because I prefer all the time that I use any theorem or an equation, I should be able to derive it from first principles. It helps somebody understand, because this one, it means I will be expecting to clearly remember some of these algorithms. This algorithm, there are many algorithms. I opted to look at this one, the Peterson-Gorenstein, I think it's Zilla. It's normally called PGZ decoding. And these guys came up with this relationship. This relationship is what we are going to use, yeah, to work out a polynomial we call the error allocator polynomial. So the concept is a bit abstract, because if you derive, of course, if you derive this, you'd see why why this is working, or how this works and why it's working like so. So if there are L errors, the relationship between the error locator polynomial and the syndromes can be expressed in matrix form like this. So these are the error locator, these are the syndromes, these are also the syndromes. So the syndrome, this is a syndrome vector, we are calling it S, and then we are having a matrix M, which is simply the syndromes organized in a certain pattern. You can see the pattern goes from S1 to SL, and here S1 to SL. Yeah. So in the matrix form, this relationship holds. And then of course you have 5L. This starts from 5L. Where L is the number of errors. Yeah. So if it's a 2 error correcting code, 2-bit error correcting code, then you're talking about L is equal to 2. So you're going to have, and this does not go. You see, this one goes from L plus 1, L plus 2. This one starts from lambda L. So, or rather, lambda 1 is here, going up, yeah, up to L, or rather L. So it starts with L minus 1, L minus 2, up to 1, yeah. So this is the equation that helps us allocate the errors. So we have this error locator polynomial. This is what we are trying to create. So we're trying to get lambda 1 up to lambda L. That will be what we will be trying to look for, and therefore get the error locator polynomials. Then whatever polynomial we get, we look for the roots of that polynomial, and that will give us where the errors are. Yeah, it's an interesting concept. It's a bit complex, but it does work. So use this polynomial to determine the error EX. So this S, which is a syndrome vector, is equal to this M multiplied by lambda, and this lambda is what we are calling the locator. This is a locator polynomial. So these are coefficients of the locator polynomial. So in the matrix form, we want to get this locator vector. Yeah, we call it locator vector. Yeah, but this is what we are trying to get in the long run. So we are saying that can be given by this. If S is equal to M lambda, therefore lambda is M inverse, and remember this is a matrix, M inverse of S. Yeah, multiplied by S. And I think the best way is we do with an example, the simple example here. I think the simple example, we understand how it really works without necessarily driving it. So we consider a 15.7 double error correction code. So we are saying that we have L is equal to 2. That's what we are saying. L is equal to 2. It's a double error correction code. And what we have, and remember we have 2 T syndromes. Yeah. So it means we're going to have 4 syndromes. We have to calculate those 4 syndromes. Yeah. So we have, let's consider this. I mean, for this code, this is a generator polynomial. For this 2-bit error correcting code, I think we have done it somewhere. This is a generate a polynomial, x to the power of 8 is x to the power of 7 plus x to the power of 7 plus x to the power of 6 plus x to the power of 4 plus x to the power of plus 1. So let's say we have this message. This message mx is 1 plus x. 1 plus x simply means this. Yeah? I just put it in this order. 1 plus x means this is 1, this is x, all these others are 0. So if we multiply this, I'm sorry, I've noticed a problem here, but I can correct it as we are going on. There's a problem here. Because actually these are x. So what you should be having, if you multiply these two, you're going to find that it is going to give you x to the 9 plus, you can multiply it out. I think is the way I wrote it here is I will explain this. Actually, this should be Rx. This should be, because actually you can see this is just the same as this one. I've only just replaced R alpha. Sorry, I'll replace R alpha here. So we have this. This is, you can multiply it out and you're going to see that it is going to be plus x to the 5 plus x to the 4 plus x plus 1. Actually, if you multiply this with this is what you're going to get. Yeah. So we are saying let's introduce errors in third and eighth position. So we are saying there was no x to the 8 and there was no x to the 3. So we are just introducing errors to see whether you will be able to detect the errors. You are going to know where the errors are. So we just introduce errors in third and eighth position. So you are going to get this. When you introduce the errors, actually this is what you get after introducing the errors. I think I wrote it badly. Yeah. So this is supposed to be the Cx is equal to, I messed up my name. So Cx is equal to Gx, or rather Mx multiplied by Gx, which is equal to this. Yeah. So just correct on your document. When I was doing it, I made a serious mistake. So that is Cx. We are saying if this was your message and with this generator polynomial, what will generate is this. But as you are transmitting it, some bits are inverted. And what we are doing is we are taking the 0 bits which are inverted and creating bit ones, because that's what it means when you're introducing errors. So you are creating this bit 1 here, another bit 1 here, which was 0. That's how you have created the errors. So you are going to get that. So we are saying that R alpha, of course, is simply this. So you're getting that. Actually, you should not even have this. You're saying you can replace alpha in this equation, but actually this is not even important to us. What is important to us is getting the syndrome. So for R alpha, because actually the syndrome is just simply R alpha. Remember, alpha is supposed to be, alpha is what we call the primitive element. and it's supposed to be a root. So we are saying this should actually work out to 0. Actually, if you try to calculate this one, it will work out to 0. Yeah. If you replaced, if you used this, okay. I think we have to go back to these fields. I think I did in another. Sorry, not that. I think I should have done it on the same page with this because it's related to this. I hope I don't lose you in the process as I'm moving up and down. Yeah. If you go to this table, you'll be able to see that here, if you go to this table, you'll be able to see that in this that this works uh, works out to 0 if you replace this with alphas. Yeah. And actually you can see that. Let's see that. I don't know how you can do that. If you replace this with alphas, what would you get? You can try to do it somewhere. Okay, so I did it. So I've done it somewhere so I can do now too. Yeah, I think we can. So I've done it here. So let's have R alpha. Let's say this is a correct syndrome. You just replace the X with the alpha, the primitive element. So we are going to find this becomes, I can write here. This becomes alpha to the 9, some of this, plus alpha to the 6, plus alpha to the 5. We are saying if this is what we received, which is the correct the correct vector, or rather I don't want to use the value vector, then this should work out to 0. And let's see, alpha to the 4, alpha plus 1. Of course, this first of all becomes a bit easy to see. You can see already alpha to the 4 plus alpha plus 1 is actually 0. Yeah. Remember that's what we used to generate this code. We used this. We used this. So we are saying this is equivalent to 0 because we did modulo this. So already we can see that this is equal to 0. So this is already equal to 0. So we are left with this. Now we need to go back to the table and find what is alpha to the 9 from this table. I hope I'm not losing you. From this table, what is alpha to the 9? Alpha to the 9 is just alpha to the power of 3 plus alpha. Oh, what have I done? Alpha to the power of 3 plus alpha. So this is alpha to the power of 3 plus alpha plus, let's see what is alpha to the power of 6. Alpha to the power of 6 is alpha to the power of 3 plus alpha to the power of 2. alpha to the power of 3 plus alpha to the power of 2. And then we have alpha to the 5. Alpha to the 5. I hope you are all following. Is alpha to the power of 2 plus alpha. To the power of 2 plus alpha. And remember we are in GF2. Yeah. Whatever the coefficient of these are in GF2, 0 and 1. So in this case, this cancels 0, this cancels 0, this cancels 0. So you can see if you replace alpha, you're going to find that this works out to 0. Yeah. So if there is an error, it will just work out to the where the error is. That's what it is. Because everything work to 0, it will only leave that particular element, which is the error. Yeah. So you can see in this case, if you do now with this particular one, if you do alpha, of course, you not just leave the error because it's going to leave two things. Yeah. So they don't. In this case, since there are two errors, it's going to leave two things. Which what it will do, it will produce like this alpha to the power of 13. So we'll produce alpha to the power 11, and this produce alpha to the power 7. Now, I did not do the calculations. I would like in your free time to do the calculation. If you do alpha for this one, it will reduce to the alpha to the 13. Yeah, you're not seeing alpha to the 13 here, but what it's going to produce is it will produce this alpha to the 13. It means it's going to come to this alpha to the power of 3 plus alpha to the power of 2 plus 1. Yeah. I hope I'm not losing anybody. So that's what it's going to work to. Yeah. That is which is alpha to the power of 13. The power of 13. Yeah. Now, if you replace in this equation such that now this becomes alpha. So it means you square this. If you replace alpha squared, it means I think this maybe is where we need to be very careful. When you talk of alpha squared, you're talking of the element, one of the elements, yeah, which of course can be broken down to they can be broken down to, let's say, what we are doing here. Yeah, we are talking of this, which we are saying is actually this. Yeah, but when we are trying to work out the alpha, we don't replace x with alpha. That's why you're seeing we are talking of alpha to the 7 being alpha to the 3 plus alpha plus 1. Yeah, and I think that's where the concept can appear a bit more abstract. Yeah. So if you replace this with alpha to the power of 2, yeah, and you replace this with alpha to the power of 2, alpha to the power of 2, alpha to the power of 2, of course you're going to get this to be alpha to the power of 18, alpha to the power of 16, alpha to the power of 12, alpha to the power of 10, alpha to the power of 8, alpha to the power of 6, alpha to the power of 2 plus 1. If you work it out just the way we have worked out for this particular valid code word, you end up getting alpha to the power of 11. Remember, you are trying to calculate the 2T syndromes. T here we are calling it L. So let's call it 2L syndromes. So 12 syndromes, you're trying to calculate the 4 syndromes. So the first syndrome is that one, alpha to the 13. Second syndrome is alpha to the power 11. If you replace this with alpha to the power of 3, so this will be alpha to the power of 27 plus alpha to the power of 24 plus alpha to the power of 6 plus, 18, alpha to the power of 15, alpha to the power of 12, alpha to the power of 9, alpha to the power of 3 is actually going to give you 0. And in all your calculation, please remember alpha to the power of 15 is what? 1. Alpha to the power of 15 is 1. It will go back to 1 here. So alpha to the power of 14 is that. Alpha to the power of 15, it's not even here because already we have the 1 here. Yeah, is 1. Yeah, alpha to the power of 15 is 1. How that makes it easier because you know what that means. If you have alpha to the power of, for example, here, alpha to the power of 27, that is simply alpha to the power of 15 times alpha to the power of 12. But you know, alpha to the power of 15 is 1. So it reduces now in this case when you do alpha to the power of 3. This one reduces only to alpha to the power of 12. Because alpha to the power of 15 is 1. Yeah? Then alpha to the power of 24 is simply alpha to the power of 15 and alpha to the power of 9. So this to the 24 just reduces to alpha to the power of 9. Next, alpha to the power of 18 is just alpha to the power of 3. It goes to be alpha to the 15 times alpha to the power of 3. Alpha to the 15, this is simply 1. When you do it to the power of 3, this one. Yeah? For this, for S3 here, it becomes 1. Then plus alpha to the 9. You can even see why it is becoming 0. There's already alpha to the 9 here. And we have seen something was alpha to the 9, alpha to the 24. Actually, to cancel with this one. Because this is alpha to the 24, which is alpha to the 9. And now this is alpha to the 9. So they will become 0. Yeah? You can see that why it is reducing to 0. So if you work it out, it will reduce to 0. Yeah?
Excuse me, sir.
Yes.
I'm having problem realizing how you come up with the receive matrix, the R of X. Would you explain how you
Or this one.
Yes.
Okay. What I was saying, yeah, that's a good question. Before we proceed, because it's going to be very difficult to understand if you don't understand that part. We are saying what we are trying to do. We are saying this is a general polynomial, and we picked just one case where the message is 1 plus x, or rather x plus 1, which is this message. Because remember, these are 15, 7. It means the code word has 15 bits, but the message bits are this, yeah, are 7. So when you see x plus 1, it actually means this, yeah. We are saying if you multiplied this and this in polynomials, you would end up with this. So this would be the correct polynomial. That's a valid polynomial. I mean, that is the correct polynomial which you are sending. Now, if you sent this over the channel and we said something changes, and we say that something, let's make it bit 3. We just want 2 bits to change. In this case, we are saying let bit 3 and 8 change. So what you are trying to do now is, if those bits change, can you be able to detect them? So that's what we are trying to say whether at last we are going to reach 2 bits which have changed. Yeah, can you be able to detect and correct? Correct means know where they are. Yeah, so it means are we able to locate, because the moment you locate that it is x8, then it, you know that is the position. That gives you actually the position. If you locate is x3, then that gives you the position. So you know it is this bit and this bit. So we are intentionally changing them. We are saying this has changed. I could have changed any other bits, but I've said let's just change these 3 and 8 bits. X to the 3 and x to the, or rather the bit which is represented by that position, by that polynomial, uh, by that in the because actually that's what these elements of these polynomials, that's what they're about. The position of the bits. If you want to know the position of the bits. So this one we simply got by adding errors. So this is an error. This is an error and this one. Because if you do this and this, you will get this. Now, what I tried to demonstrate at the beginning is when if there is no, if you do actually the syndrome, the first syndrome is simply add alpha. The second syndrome is R alpha squared to the power of 2. The last syndrome is alpha R alpha to the power of 3. And what you mean by that is maybe in these ones, you replace the x with the alpha squared, is you replace x with alpha squared. For alpha to the power of 3, replace x with alpha to the power of 3. For alpha to the power of 4, replace x with alpha to the power of 4. X, not, so it will be x to the power of 4 to the power of 5. No, this is 9, sorry. The power of 9, it's not 5. Are we clear? Did I answer your question now? Yes. So we are trying to find out what are these syndromes. So if there are only 4 syndromes, you don't only go to alpha to the power of 4. If there are 6 syndromes, you go up to alpha to the power of 6. So it will give you S for R. And if you talk this, if you try to work this out, considering this, it will simply work out to alpha to the power of 13. Yeah. And of course, you are wondering how is the alpha to the power of 13 coming in? And this does not even have x to the power of 13. It is because alpha to the power of 13 means what you are going to end up getting is this. And when you get this, that is alpha to the power of 13. Yeah. I hope that is that's clear. That's what you're saying. So for alpha to the power of 4, this is S4. I think this is S4 is simply R alpha to the 4. Just replacing the receive syndrome X with alpha to the 4. So if you put alpha to the 4 here, this will become alpha to the 36. But alpha to the 36 is alpha to the 15 times alpha to the 15 times alpha to the 6. So it will simply become alpha to the power of 6 because alpha to the 15 is 1. So 1 times alpha to the power of 6. So for this case, this will simply become alpha to the power of 6. This is alpha to the power of 24. No, 32. So this will just be alpha to the power of 2. Alpha to the power of 2. I think you can see that. So this becomes alpha to the 32. This when you put alpha to the 4, to become alpha to the 32, and that is because of alpha to the 15, that is simply alpha to the 2. In fact, why don't we do for this one? Maybe it will make some sense. So the first term, due for this, see how you get alpha to the 7. So if you do for alpha to 4, this will become someone wants to join. I'm trying to see where that is. Yeah. Let's do for this particular alpha to the power 4. I should have really been pages to do calculations. I don't have space for calculations. So this will become, we have seen, I hope you're able to follow that without me writing. If you do this to the power of 4, this becomes to the 36, which because alpha to the 15 is 1, that becomes 15 times 15, 1 times 1, so it becomes alpha to the 6 plus alpha to the 8, we found is alpha to the 32, so it becomes alpha to the power of 2 plus alpha to the 24, because of alpha to the 15 to become alpha to the 9, because alpha 24 is simply alpha to the 15 times alpha to the 9, plus alpha to the 5 is alpha to the 20, which is alpha to the 5. It will simply become alpha to the 5, because times 4 is 20, alpha to the 15 is 1, it's alpha to the 5, plus alpha to the 4 is alpha to the 16, which is alpha. Yeah, we do this alpha to the 16, which is alpha to 15 times alpha, to this alpha. This alpha to the 12, plus alpha, this alpha to the 4. Nothing is cancelling outright, plus 1. Although, of course, I can see this one is getting finished. This and this and this. That is equal to 0. Yeah, we are seeing that because that is a polynomial which we used to generate the elements. Use that polynomial. So that polynomial must be equal to 0. Yeah. Now, to see how these others can work out. Let's look for that. Now, what you have to do is get this go to so we have alpha to the 6 plus alpha to the 2 plus alpha to the 9 plus alpha to the 5 plus alpha to the 12. I'm going to this table and I'm finding alpha to the 6 is alpha to the 3 plus alpha to the 2 plus I think you're doing the math with me because I'm not writing it here, but I'm just writing on my table to see what that will come to. But I just want to do it together. Then alpha, then there's alpha to the 2, yeah. Alpha to the 9 is alpha to the 3 plus alpha. Here, alpha to the 9, alpha to the 3 plus alpha. Alpha to the 5 is alpha to the 2 plus alpha. Here. Alpha to the 12 is alpha to the 3 plus alpha to the 2 alpha plus 1. So we want it to come out as, okay, let's see. If you are working with me, I'm trying to cancel out what can cancel out. I think there is all the alpha to the power of 2 cancel out. Alpha to the power of 3 also cancel out. 2 of them. alpha and alpha cancel out. So I'm remaining with alpha to the 3 plus alpha plus 1. Alpha to the 3 plus alpha plus 1. Oh, which is 7. Yeah? Let's check whether we got alpha 7. Yeah. So I hope everybody was able to do that by replacing what we got here, this ones here, with substituting from the table. Yeah. Well, let me, maybe I just write it here for this. Maybe somebody did not follow. What I did is I found that alpha to the 6 was alpha to the power of 2, no, alpha to the power of 3 plus alpha to the power of 2. Then I went to alpha, and then of course there is alpha to the 2 following there. Then there was alpha to the 9, which I found was oh, on my left last page I'm lost. I think I hope it was. I'm see what I had done without going back to the page. Plus alpha to the 3 plus alpha. I think that's what alpha to the 9 is. And then plus alpha to the 2 plus alpha. That's alpha to the 5. And then alpha to the 12 plus alpha to the 3 plus alpha to the 2 plus alpha plus 1. So what I can't this and this. I cancelled this and this. I cancelled this and this. I cancelled this and this. So I remained with this, this star and this star, and that is equivalent to alpha 27 from that table. So is it okay? Now, yes, because you only have up to you have S1, S2, and because it is here, you go to this here. S1, S2, we have two S. So the maximum you get is S1, S2. This is S3. So the maximum you can get is this S1, S3. Of course, those are there. So we are not even using the fourth syndrome. Yeah, alpha 7. It doesn't even, we are only using the 3 syndromes in the M. So in the M, we are getting this. S1 is alpha to the 13, S2 is alpha to the 11, S2 is alpha to the 11, S3 is 0 here. So we are only using this, we are not even using S4. Yeah. So for L is equal to 2, that is our matrix M. Yeah. Now, what we need is M, because you want to calculate lambda. Yeah. You want to calculate lambda. Then, so to get lambda, you must do the inverse matrix. And of course, I think you're familiar with doing that. So we do the adjoint of the matrix M. Yeah, adjoin. I think it's called adjoin. Yeah, adjoin of matrix M, which, if I remember my matrix, it simply means interchanging these two and then negating these two. I think if you have A, B, C, D, I think if this is M, the adjoint of, I think the M, adjoint of, what's the word adjoint? Is simply this adjoint, adjoint, is simply D A minus C minus B. I think that's what it's supposed to be. I'm not sure you can remind me. I don't want to do this recently, but I think that's how I. But of course, you're in binary, so we just write alpha to the 11 instead of the minus alpha to the 11. Yeah. And then we get the determinant. Determinant is normally AB minus AC, is it? Determinant should be this minus this. Yes, I think that's what it should be. So that should be what am I getting? Oh, we got that. I'm going to get this, what I'm going to get. 1 over this determinant. Yeah? No, so the turning point is for determinant of M. Determinant of M should be AD minus BC. I think that's how it should be. AD minus BC. So BC are these ones. So this is alpha to the 22. Yeah. So this should be 0 minus, in this case, we are talking of 22. So we have alpha to the power of 22, which is simply alpha to the 15 times alpha to the 7. But alpha to the 15 we know is 1. So that's how we are getting alpha to the 7. Yeah. You can see how important that table is, because if you don't have that table, then this will be very abstract. You will not understand how to get this. You could have put alpha to a 22. Of course, later it will still work out the same thing. You are going to cancel out later, but this becomes alpha to the 7. So that's what we have. And so if you divide this alpha to the 7, we are going to get alpha. This will be 0, this will be alpha to the 4, alpha to the 4, and this will be alpha 6. Yeah. So the inverse matrix M is that. Then S, let's see where we're headed. So S, in this case, we are talking of Si plus 1, the syndrome vector. We are talking of Si plus 1. This one here. We are going back to the PGZ formula. So this becomes Si plus 1. Where are we? You are here. So you simply S2 plus 1 is S3, and Si plus 2, which is S4. We can't go to nil. We have only 2. Yeah. So we are saying that will be equal to, we know S4 is alpha to the 7, and S3 is 0. So now we can be able to get our lambda. What we want is the lambdas. Oh, I don't know why I put this. I think I wonder what I'm doing this one on kind of. Because remember the lambda is just these matrices starting with the highest going lower. So we are saying lambda is simply this times this, and that works out to alpha to the 11 and alpha to the 12. So our locator polynomial is this one. We are simply, this is a general form of the locator polynomial. In our case, it means this. Yeah. I think I should not have used alpha, I should have used alpha here. Sorry. If you have the lambda, you should have used, oh, we're using lambda. You should use alpha. I'll get mixed up with this. This should be, this is a general form. This is our case. Yeah. So about this, cancel again. I think I made out a mistake with this one. I think I was writing faster. So this is alpha to the 13 and alpha to the 12. So all you need to do is factorize this. Yeah. And we are saying you write, yeah, because to factorize, you know, to factorize it means this should be what? It should be that you look for two numbers, the product of two terms, giving you 13. And when when you add them, you get 11 when you multiply here, and when you add them, you get 13. Yeah. So you are looking for two numbers which, when you add, they give you 13, and then when you multiply, they give you 11. That's an interesting one. And you're going to find that it is just alpha 8 and alpha 3. Alpha to the power of 3, alpha to the power of 8, and alpha to the power of 3. They will give you alpha to the 11 when you multiply them. When you add them, they will give you alpha to the 13. You can try to find out that. Let's look at, of course, this is where it is complicated. We need to go back to the table. What is alpha to the power of 8? It is this, and alpha to the power of 3. Yeah. So if you add these two alphas, it will be, alpha to the 8 and alpha to the 3 to be alpha to the power of 13. It will be this one here. If you add these two, you can see, if you add these two, they are the same as alpha to the 13. Yeah. So we have solved. We have found that actually we can get two. We can get these two, and they will give you what we got from this. So factorizing the error locator polynomial is able to give us the bit error position. So it is alpha to the 8 and alpha to the 3. And you remember that's where we had put the errors. So we are saying this method can actually work. It works, and we did with an example. We placed errors in these positions, and now we are able to find that actually the errors were in this position. Yeah, because now these are the errors. So is that okay? I know it's a but I thought it's good that at least you have an idea of the concept of decoding BCH codes. It's complex, but of course, to when you try to, its implementation is easy, as difficult as it looks with these formulas. When it comes to the implementation, it's quite easy with the hardware. Eric,
Yes,
yeah.
I wanted to ask you, how are you determining the power of alpha when you want to work on when you are multiplying the power of alpha with the generated code word? Because you've chosen the value of the power of alpha to be 4. Do you choose it arbitrarily, or what is the guide there? Because when you are dealing with the
Mm.
when we are dealing with the block codes, we told
Mhm.
us that the number of syndromes is
Mm.
something the same as the number of errors in a code word.
This alpha, I think it goes back to, you know, I'm decoding, so I'm still following this. This, the ones we use to generate these elements is the irreducible polynomial, which we call a prime polynomial. It's reducible polynomial of, uh, you see that these are four of degree m, where m is this number of bits. Actually, where m is, remember this GF16 is simply GF2, because we are dealing with binary, 2 to the m, where so m here is equal to 4. Yeah, because it is GF of the prime number to a power m. And for us, actually, we can still do it with the GF3. It will still work out, but for non-binary codes, yeah, where we are using Galois field 3. So we'll be now doing 3 to the power of 1, 3 to the power of 2, 3 to the power of 3. So the one which we used to generate these elements is any irreducible polynomial of degree m. Yeah, and they are quite a number actually. Uh, I think if you go to the internet, it might even give you the polynomials of degree 4. I think of 4 are not so many, but like for example, of degree 5 are very many. If you are dealing with GF32, then you'll be looking at polynomials of degree 5. Those are the ones you use. For GF16, use as irreducible polynomials, which you cannot reduce. They are prime. They are, yeah. So you'd use uh, whatever is. So this is not very arbitrary. Is they are actually, you can calculate them. Yeah, they are given. Actually, I've seen. I think even most textbooks will give you all the polynomials of degree 4, which are irreducible, and they can also give you all the polynomials of degree 5, which are irreducible. So you can use any of these to generate your field elements. Of course, the field elements will be different, but one thing will happen is, what even if they are different, it's just the order, but they will produce all these, whichever one you use. They'll make sure that they produce all these different combinations of ones. You can see none of this is repeated. Yeah, I don't know whether I answered your question, or whether that was a question in the first place.
Yes, thank you.
Okay, thank you very much. So it's not arbitrary. Yes, Soba, Yusuf. Yusuf, you raised your hand. I don't know why you pressed by mistake.
I was asking in the previous example, how did you, the message was 1 plus x, how did you convert that to binary?
Oh, how binary? Okay. What I did, where was it? I think it was this one right here. No, I think it was no, it was the example after this. No, it was before this. It was here. Yeah, is this one? Okay, I wanted to put in the. Okay, sometimes we write 1 plus x. That was wrong. I should write x plus 1. I should be consistent. Yeah. If I write from the highest, then I need to be consistent. So it is x plus 1. So, of course, if you convert to binary, it actually means, you see, there's supposed to be a message of 7 bits. It actually means why is x plus 1 is because the, uh, the, the coefficient of x to the 2 is 0. The coefficient of x to the 3 is 0, x to the 4 is 0, x because it should be up form. It should be x to the 6, x to the 5, x to the 4, x to the 3, x to the 2, x to the 1, x to the 0. So it means all these others are 0. That's why you don't put them. Yeah. So why I came with this is because it has to be a 7-bit message, 157. Did I answer your question?
Yeah.
Okay, thank you. Thank you. So let's go to RS codes. Let's have, yes, Samuel.
Yes, I was kindly requesting if you could maybe give us 5 minutes to stretch and then we come back.
Uh, 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 Samuel, you just read my mind. That's what I was going to give you. 5 minutes, then we come back because I can see it's half time. So let's meet here at 8:35. Okay? 5 minutes.
Thank you.
I think we have had our 5 minutes. We had more than that. So we are going to look at a group of codes which are group. I mean, they are BCH. They are binary, non-binary BCH codes. Yeah. So we say they are subclass of BCH code with a wide range of applications in digital communication and storage. Actually, these codes can be used for storage. And actually, why particular storage is because they are very good for not just for checking for code. I mean bit inversion. Then they can actually be able to check that the bits are erased. The bits are not there. Yeah, they're able to detect bits which are not there. Then, which is erasure. So basically, they can be considered to be like erasure codes. Yeah. These were invented in the 60s. That's why they are called the Solomons by these two guys, Alvin Reed and Gustav Solomon in MIT in 1960. Fairly new. I mean, some of the things we're learning are things invented in the 15th, 16th century. This is just last century, 20th century. Yeah. So the Solomons codes are used to correct errors in many systems, storage devices. They are used in CDs, especially when CDs are scratched. You tend to lose quite a number of bits. You get burst errors. And some of these can correct up to 16. I mean, if you're talking about 16 symbol errors, and let's say you're using symbols of 8 bits, you are saying you can correct 168 bits. Because these 16 symbol errors could just be following one another. Because again, you see, a symbol error is if any bit in the symbol is in error, that's a symbol error. If all bits in a symbol are in error, that's still one symbol error. Yeah. So, for example, let's just look at the case whereby maybe I can just give a small explanation. Maybe you're using 3-bit symbols. So maybe the symbols are 101, 111, 011. So these are our symbols. So this is S1, S2, S3. So these are our symbols. You're not looking at bits. You're looking at it from a symbol. So these are your symbols. You're grouping bits into symbols. So if you can correct 3 symbol errors, that can mean all the symbols are in error. It means either it is 1 bit is in error here, 1 bit is in error here, 1 bit is in error here, or 2 bits are in error here, or all the 3 bits are in error. So if you can correct 3 symbol errors, then it means you can correct 9-bit errors. Yeah, if they happen to be where you have completely all the bits are in error. Yeah. So that's what makes it possible to be able to do burst errors, because you can imagine you can have 3 symbols and everything is rubbed out. Codes or the binary BCH codes. That could just be one simple error in the Solomon code. Yeah, I don't know if I'm making some sense, but I'm trying to say that's why what makes it very, very, very amenable for, especially where you're expecting vast errors. That will be places like storage devices, wireless communication, I think satellite communications, especially satellite communication, because I think this is wireless is more general and satellite is more specific. Yeah, because wireless will include even radio LANs, that's radio wireless LANs. It also includes terrestrial microwave, but also the satellite communications, especially satellite communication, because you are traversing a long distance, 1,000 kilometers. So sometimes you expect quite a lot of errors, and so you need something who can be able to correct a lot of bit errors. Yeah. Digital television, yeah. Digital television is another area. I'm trying to see why it will be you'd use this other than the ordinary BCH or yeah, but where you expect a lot of errors, especially vast errors, is where we apply mainly the Solomon codes. So at the transmitter, just like in the other case, the Solomon encoder takes a block of digital data and adds redundant bits. Actually, digital data and adds redundant bits. Of course, we are looking at this more redundant symbols other than bits. Errors occur during transmission due to noise or interference, and storage due to scratches, example CDs and DVD. At the receiver, the Solomon decoder processes the block and attempts to correct the errors and recover the original block of data. The number of errors can be corrected based on the characteristics of the RS code. Yeah, I think that applies to all error correcting codes. Yeah. So what is their properties? They are linear block codes specified as RSNK with S bit symbols. Now the S bit is like what you are seeing here. Here is 3-bit symbols. So the S is like 3 here. With S bit symbols. That is the encoder takes K data symbols, not data bits, data symbols of S bits each, and adds N minus K S bit parity symbols to make an N symbol password. The same thing we are doing, we are taking K message bits, adding N minus K parity bits, and then creating an N bit code word. Yeah. So here we are creating an N symbol code word. The Solomon can correct errors and erasures. Errors is where you're expecting a 0 and you get a 1, or where you're expecting a 1 and get a 0. Erasures is where you don't even know what was supposed to be. But the beauty about erasures is you know the location of the errors. Yeah. When you know the location, but you don't know which bits. Yeah. So someone can correct up to T symbols that contain errors in the code word, where 2T is given by n minus k. That is important for the Solomon's code. And a decoder can correct up to a decoder can correct up to 2t erasures. Of course, an erasure occurs when the position of a missing symbol is known. That's what it means. You know where the missing symbol is. So the distance is given by n minus k plus 1, and we are saying for Reed Solomon's codes, you can get this equality. When this equality, the equality now, not the non-equality, when d is equal to n minus k plus 1, we say that code is this is a singleton bound formula, yeah, and we are saying when this is equal to this, you get a maximum distance separable code. So we say this with the Solomons, you can be able to choose our this way also what you can get MDS, maximum distance separable codes. Yeah, that just means this singleton. I think this is a fellow who was called singleton. So when you talk about singleton bound, we are saying this formula applies. The distance between the formula and n minus k must always be n minus k plus 1 must always be greater than d. Yeah, must be equal or greater than d. But when it is equal to d, then we say that code is a maximum distance separable code. Yeah, we will not get into that theory that when you get that, that's the most efficient code. When that's the highest degree of efficiency you can get from a code. Yeah, when you have the maximum distance separable code. Yeah. And you can see we are saying that's the best distance you can get, because it's supposed to be less, but when it is equal, that's the best distance you can get. And of course, the distance determines the what? The error correcting capability. That's why when you can get the maximum distance, you are very happy, because then you are able to correct more errors. Yeah, because error correcting capability depends on the distance. Yeah. So some of the popular Reed-Solomon codes is this one, which was used with 8-bit symbols. We talked about S-bit symbols. S here is equal to 8 in Voyager 1. So of course, N is 255. You have 8-bit symbols. It means you can have 255 different code words. So these were used in Voyager 1. So in the RIS 255, 223, each code word contains 255 byte code word. Actually, this is 255 bytes. And of course, we are calling it bytes because they are symbols. They are 8-bit symbols. So in this particular case, these are bytes. Yeah. So it contains 255 byte code word. And we're also saying, since we have 8 bits, your symbol can be one of the 255 symbols. Of course, that 255 is different from this 255 because you are talking about 255 byte code word, of which 223 bytes are data and 32 bytes are parity. It's good to know that we are using bytes here because they are 8-bit, and 8-bit is a byte. Yeah. So this parity, so the length, this code has a length n is equal to 255, K is equal to 223 and S is equal to 8 in our case here. So the number of errors can be corrected. T is equal to 16 because of this 32-bit. Because you're saying n minus k, 2t is equal to n minus k. Yeah, n minus k is 32, so you can correct up to 16 symbols. Yeah, 16 symbol errors. You can correct up to 16 because of this formula here. The decoder can correct any 16 symbol errors anywhere in the code word. Yeah. So you can be anywhere in the code word. It can be any bit in the code word, or it can be all bits in the code word. Yeah, these 8-bit code words. But you can correct 16 symbols. Rather, what we are saying, suppose you have 16 symbols. And it's you can see why it can be very good. You have 16 symbols, and those 16 symbols, each is 8-bit, and they are following one another, those 16 symbols. So you are talking about, you can correct 16 times 8-bit code word. Yeah, I mean, you can correct 148 bits in your message if they are in errors. Yeah. So for a bit, for symbol size S, the code word length is 2s, 2 to the s minus 1. You can see the code word length has to be related to s. I mean, for this system to work. So you can only have the code word length of 2s to the minus 1 bytes. So it's not arbitrary. We cannot use, because of this s, we have to use n is equal to 255. So depending on the number of, so if you use the read date, then the code word length has to be 7. Yeah. So the length of a code with 8-bit symbols is that. I think that is very important to note that. It goes to work with all RS codes. Otherwise, it won't work with the formulas, what we have learned so far, with the use of minimal polynomials. Now, it's interesting, of course, we can have what we call shortened Solomon codes. Instead of the 255, we do what we normally do is get the shortened code, which is you use you take 168 message bits, you add 55 0 bytes. I think that will give us the 223 messages, and then we create this 255 by 223 code word, and then transmit only the 168 bytes and 32 parity bits. It's an interesting concept. What you're doing is you can transmit fewer bits and still be able to enjoy the capability of this Reed Solomon code, the 255 bit. So it's an interesting concept. You are taking the 168 message bits, adding 55 0 bytes in the message, so that you create a 223 message these bits, So what you generate, so you add that, so what you're able to generate the 255. Now, once you generate 255, you don't carry the 55, the ones you added, the zeros. So you only carry 200. So what you're saying is what you're transmitting is just this, and then at the receiver, you add your zeros back. It's a way of preserving the channel. I mean, carrying less bits, or rather increasing efficiency. Yeah. So that is normally called the shortened Solomon code, the 200 by 168. It has the advantage that it increases the efficiency. You're carrying fewer bits and enjoying the same error correcting capabilities. So symbol errors can occur when one bit in a symbol is flipped, or up to all the bits in the symbol is flipped. I think I've talked about this. When you talk about symbol error, it can just be one bit in that symbol, or it can be all the bits. For example, the 255, 223 can correct 16 symbol errors. This may be 16-bit errors, each in a separate symbol, or it may simply be 16 times 8-bit errors. Yeah. So it can correct. That's why you can see it's very good for burst errors. Because when 8 bits are erased, that's just a symbol error. Yeah, actually, it's said here. The Solomon codes are particularly well suited for burst errors. So the Solomon's code words are generated using a generator polynomial, just like in all other BCH codes. So our main work is just to find out exactly how do we generate, how do we construct our generator polynomial. Because at the end of the day, the code word you send, you simply multiply the generator polynomial with the message polynomial. And the GS, the generator polynomial, and MX is the message polynomial. The generator is of the, now, with these ones, unless unlike the case where we're trying to look for the LCM, in the case of the BCH codes, we are looking for the LCM of the of the minimal polynomials. Here, in this case, each of the elements have a different minimal polynomial. So you are going to multiply just this. That is g of x is x minus a alpha to the I into x minus alpha to the I plus 1 up to x minus alpha to the I plus 2 minus 1. This is a general one. All it is saying is that, of course, when you see alpha to the I, you get confused, but it can simply be I is equal to 1. So you start with alpha to 1, I is equal to 1, alpha to the power of 2 up to alpha. If I is equal to 1, this becomes alpha to the 2t. Yeah? Where t is the number of errors to be corrected. Yeah? That's how you generate, that's how you construct your generator polynomials. And let's see. Okay, I think we have, let's do with a simple example. Here we are saying, actually we are using the same table. I've just used Z, doesn't matter, I could have used alpha. And I could have used X. Yeah. But we are saying, let's consider cases whereby you have got 8, you have got you're using 3 bits. You're using symbols with 3 bits. So these are the possible symbols. Yeah. You're using symbols with 3 bits. and we look at this case here. Example, in GFQ theorem, the minimum polynomial for any element alpha I is given by x minus alpha to the power of I. Therefore, gx here will simply be x minus alpha to the I into this. I think that's what we have just seen up there. The degree of gx is 2t. Yeah, because of this 2t. So this will start with x to the power of 1 up to x. I mean x minus alpha to the power of 1, and this x minus alpha to the power of 2t. So the degree of this gx is 2t. N, the length of the code word, is q to the n minus 1. And in this case, of course, it means which. Why you are talking about q? In our case, q is 2. Yeah? In our case, q is 2. We are limiting ourselves to where these are binaries. The symbols are made of binary bits. Yeah? So we are doing with GF2. And actually, you can still use other GFs to create these RS codes. But let's deal with the case whereby these are binary, because in any case, we are transmitting binary. Even when you use the others, you still have to even if you use others, you still have to convert to binary. Those are bits are in binary. Yeah. So so you have this created with this polynomial px. So alpha is the root of this. Yeah, we know that. Just like in the case of also we are using this just in the case of the binary PCH codes. So px is equal to that. Therefore, gx is equal to this. So our generator polynomial is equal to this. Yeah. For this case, where you have got where you do GF8, GF2 to the 3. So our generator polynomial will be that this will generate a 7, 3 RS code. The B mean is equal to 5. Because remember, N, how many errors do you want to correct? I think it is the number of errors we want to correct. Yeah? We want to correct single bit error. Yeah, we want to correct 2 errors. I think we must have specified what we want to correct. We want to correct 2 errors, so n minus k must be 4. So it looks like k is 3. So it's a 7, 3. I don't know whether I specified somewhere. Yeah, we want to correct. Yeah, we went up to alpha to the 4. So we want to correct 2 errors. I think I did not mention it here. The degree of gx is 2. I didn't mention. So we want to create a code which can correct 2 errors. So 2t is equal to 4, and that's why we are having our generator polynomials having 2t. Yeah. So this generator polynomial will generate a 7, 3 code, because 2t is equal to 4, and n minus k is equal to 2t. So it all depends on what you're trying to correct. Yeah. And if you have a distance of 5, I think we calculated the distance of 5. And actually, this is an MDS code. Remember, we said the distance must be equal or less to n minus k plus 1. So actually, in this case, d is equal to n minus k plus 1. You can see what you're seeing is an MDS code there. Yeah. Maximum distance separable code. It fulfills this. So let's do a small example. It will become a bit clearer when you do a small example. Let's look at this case. You have a sequence 110 001 011. So this is a sequence which this is a message. I mean, this sequence is what you transmit. This is your IX. Yeah. Remember, our sequences have got 3 symbols. Our sequences have 3 symbols because these are 7 3, and we are talking about 7 symbols, and these are 3 symbols, not bits. Yeah. So these are our sequence with 3 symbols. See, the symbols have to be different combinations of zeros and ones. So these are sequence, and sometimes when we want to show is non-binary, we can replace them we can replace them with decimal. So it is a 6 1 3. This is 6 in decimal. 6 1 in decimal, 3 in decimal. Sometimes when you want to show that it is not a binary code, you convert this into decimal. So in this case, IX is Z squared plus Z. This one, IX is Z squared plus Z x to the power of 2. Yeah. Plus X. This is simply X. And this is Z plus 1. Yeah. Because this is just 1. So this element here, I mean this symbol here, is just X. Yeah. Because this is supposed to be the coefficient. Yeah. The coefficient of this is that. The coefficient of this is just 1. Yeah. The coefficient of this is Z plus 1. This is Z plus 1 into 1. Yeah. Because we have X to the power of 2 plus X plus 1. So that's the coefficient. So this is 1 times this, so the coefficient is 1. This is just X. Yeah. Where it is just X. So this is just 1. This is a coefficient. The coefficient is 1. This is 1. This the coefficient is 1. The coefficient of this is Z squared plus Z. And the coefficient of this is 1. The coefficient of this is Z plus 1. I hope we are able to understand that. We don't have that confusion. But now, from this table, from this small table here now, you can be able to get that as alpha to the 4 x squared plus x plus alpha, because this z squared plus 2 is just alpha to the 4 here. Right, this table was here. This one, z squared plus z, just alpha to the 4. Yeah. This remains the same. Z plus 1 is alpha to the 3. Z plus 1 alpha to the 3. So we are saying this is just this, and therefore Cx is equal to Ix times Gx, and so you multiply this out, and when you multiply out, you end up getting this. Yeah, you end up getting this, and eventually you are going to get this. Yeah, I think this, you're going to get this. Well, if you multiply these out, this is what we are going to get. Things will cancel out one another, so you end up with this. Yeah. So we are saying our output sequence is These are the 6 sequences. I mean, this is the output sequence is 7-bit. I mean, it's 7 symbols, sorry. So the first symbol will be this one. Remember, this alpha to the 4 is Z, is this Z what? Z squared plus Z. That's what here. We must always go back to this symbol. Z squared plus Z. Alpha to the 4 is Z squared plus Z. This alpha to the 7 plus 1. Oh, not there, is here. X to the 5 is 0. So this next symbol is just 0. This one is alpha plus alpha squared plus alpha. It is this symbol again, the same symbol. Then x to the 3 is 0, so just 0. X to the 4 is 0, so there's 0. X to the 5, x is alpha squared plus 1. So alpha is 0, so it's alpha squared plus 1. And the last one, of course, since there is no 1, so it means that one is 0, 0, 0. I hope everybody by now understands how we are getting this. Yeah, it's supposed to be 6-bit. So, and they're supposed to be, there are supposed to be 6 symbols, and each symbol is supposed to be the coefficients of this polynomial, and the coefficients are in this form. Yeah, they will be, when you get alpha to the 4, you have to go back to the table and find what is alpha to the 4. You find it is Z squared plus Z plus Z equal plus Z. This coefficient is 0, so just 0, 0, 0. This coefficient is alpha squared plus alpha, which is actually the same as this. Yeah, but you see its position is given by this, and this one, this position is 0, so that is 0. This is 0, that is 0, and this is 1, 1. And of course, there is no 1, so it means that this is simply plus 0 times 1. Yeah, put there. So this is 0, 0, 0. So in binary, it becomes, these are the binaries. If you represent them in decimal, it's simply 6, 0, 6, 0, 0, 0, 5, 0. Yeah, the 7 symbols. So that is Solomon's codes, how you decode. We won't get into the decoding of the Solomon codes because it becomes absolutely more complicated. We have to use another, but it is similar to the binary BCH decoding. So in this case, it looks like it's even easier to calculate the generator polynomial. You simply look up to, you simply do x minus alpha up to x minus alpha to the 2t. So this can actually be able to detect 2 symbol errors. It means 2 symbol errors can be corrected. There are 3 symbols. You can correct 2 symbols. Those symbol errors can mean 1 bit going wrong of all the 3 bits going wrong. Yeah. Any question on this one? I think at the end of we will look for a day, then we can do again as what we did with the others, where we can have a physical class and go through a number of examples. Now, this is what I intend to do. We have 4 weeks remaining. These 4 weeks, we are supposed to look, actually the syllabus is we are supposed to do an analysis of a communication system, and we agreed that the system we are going to analyze is a computer communication system for many reasons. One, I believe it is one of the ones you have to study a minimum. To be able to evaluate a system, you need to have done quite some theory. And when I looked at the systems, the possible systems, you can look at this. I think we were given 3 alternatives. You can look at the television system. But I looked at it, if you do a television system, you will need to cover more theory for only a third of this course. So we have been choosing this computer communication system, and that's what we are going to do. So how we intend to do it, we need to cover a certain minimum amount of theory, because in computer communication networks, and from what I've been gathering from the other classes and also your classes, you did introduction to computers, but you did not go deep into computer networks. So what we are going to do for the next 4 weeks, or let's put it 3 weeks, we are going to look at different aspects of computer networks, or rather the ones I believe with that minimum theory you can be able to design a network. And analyze, and we can do that as our assignment. Of course, where I was told is I wanted to give you assignment quite early. I wanted that to be the assignment part, but I wanted to give you assignment quite early. But if you have not done enough theory in computer communication, that may be quite a tall order. Because I wanted to do it, then you can also combine with, at the end of the semester, maybe in the last week, you can have an online session where you present the system you have designed. We wanted to see whether we give you enough theory. We have not done it before we have actually just done the normal assignments. We go through the computer topics, computer network topic, and people understand. And but this time I want us to do it a bit differently. I want us to be able to actually design a small network, yeah, and present it in the class. I think it will give us more understanding of a computer network. And makes you try to design a network, no matter how small it is. It gives you and it's important because at the end of the day, once you leave here, especially for us who are not running very complicated communication systems, one of the communication systems you're going to meet almost everywhere is a computer communication system. Yeah. So if you're doing an organization, probably you'll be the guy who is expected to sort them out when it comes to the network. Either you join as the IT department, or you join in telecommunication. In most big organizations, they have a separate telecommunication department, but you find you'll be dealing with the networks. In smaller organizations, they just have an IT department which handles telecommunication and also the IT. Yeah? So with that said, if you don't have any problem with the the little we have covered about RS codes, I think the best way to cover this is maybe to do more examples, which I'm thinking we can do. We can do these examples later. I want us to just to look at something. I've sent you network protocol architecture. Basically, that is learning about the OSI model. Because I believe if you are to do anything in networking, you start at the networking models. Actually, the moment you learn networking models, you are ready to do any network, even without any theory. The rest, networking model is actually the base of networking. That's why you all start the OSI model. But before we do that, I wanted to just introduce a small a document. I think I not sent this one. I was thinking it's very basic. Is just an introduction to computer networks. By the way, I didn't ask you, does anybody have a problem with so far with what we have done? So
Yes,
that
please. You can maybe just repeat how you got an I of X and
oh,
that clearly.
how did I get I of X?
Yeah.
Oh, this I of X, you're simply saying this is a message. This is a message sequence you want to send. You see now our message has to have 3 symbols, eh? So I'm looking at a case whereby this is what you are to transmit. This is actually your message. We want to know what will you transmit. Yeah. So what you will transmit is what we are going to use the generator polynomial, and this generator polynomial we had locked it up here. We locked up the generator polynomial is this one here. I think this is the one for this particular, for the case where you want to correct 2 symbol errors. It works out you can only have 3 symbols because the length of your sequence will be 2 to the m minus 1. Yeah, n is equal to 2 to the m minus 1. Remember the case of the 255 symbols, but it's because you are using 8 symbols. So it is 2 to the 8 minus 1. So this is 2 to the n minus 1. So n minus k. So this will it will be a 7 3 symbol. So we are seeing the symbols we have in our case is S1, S2, and S3. Those are our symbols. Yeah. We have 3 symbols. But those 3 symbols will be just be combinations of these bits. And we are saying these combinations means this is, see, this is Z squared plus Z plus the one part is just 0. Yeah. Because of this, yeah. Z squared, this one's here. So like when you say Z squared plus Z, it means this part, other part is 0, yeah? So Z squared plus Z. So our symbol is Z squared plus Z, X squared, because these are 3 symbols, eh? Since there are 3 symbols, one will be represented by the one position, the other one by the X position, and the other one by the X squared position, yeah? These are the 3 symbols. That's why I'm putting 2 variables or 2 indeterminates, Z and X. Because this one is the position of the symbol, and this is the position of the ones in each symbol. Yeah. So these are the symbols, and this is the position of the ones in each symbol. So the position of the ones in this case, actually, this is, you see, this is 001. So it's just 1 because it does not have the Z squared part, doesn't have the Z part, so it's just 1 X. So that's the position of this symbol. and this is the position of this symbol, because these are the very positions. That is that position, that is that position, and that is that position. Yeah, these are the S1, S2, S3. So that's why you're seeing this I to the X is equal to this. Now you must put this in terms of alpha. Yeah. So in terms of alpha, that is alpha to the 4. We are just working from this table here. Yeah. Plus X, 1X, plus Z plus 1 is alpha to the 3. Yeah. So our sequence is that. You can see we are putting it in the same format as the generator polynomial. So we are multiplying this to the generator polynomial. But I think I've already answered your question, because I think your question was how do you get this to be this? And I answered your question, Samuel.
Thank you, sir. Absolutely.
Oh, it was very okay. Samuel, you have put up your hand.
Yes, I have 3 kind of general questions or concerns that I was hoping to ask after you've done with the lecture.
Yeah.
I can go ahead.
Yes, go ahead, please.
Yes, the first one was, I think it was last year, but one Voyager 1 had some issue. I don't know if it was with the memory, and it was transmitting some data that was deemed to be garbage. So I was wondering why the correction, the Reed Solomon code was incapable of correcting such kind of error that was happening.
Oh, that's an interesting one. So they are saying the error correction code did not work.
From the article I read, it had to do something with a memory section of the Voyager being corrupted. So it was transmitting a signal that was carrying some garbage data.
Yeah, I think, you know what I'm thinking. If they were able to detect that that is not the correct data, then the means the system was working. Yeah, because you're saying they were getting garbage. It means, because you see that the worst case. But I see what you're saying. Maybe the system is not able to correct. The worst case is accepting data that is. Oh, of course, what can happen? No, now that you say it, I can see what happens. You see, when you say a system can correct, let's say, like this Voyager is supposed to be correcting 16. Yeah, and I think that's what must have happened with the Voyager. It's supposed to correct 16 symbol errors. It would mean that you're getting errors which are over 16 symbols, so it will not be able to correct. You know, the assumption with correction is that the correction will be the symbol errors will be less than the capability of that. So of course, if there's some problem with the memory, it means the whole data is corrupted. It means you're not having 16 symbol errors in the 255 symbols. It means in the 255 symbols, more than 16 symbols were in there. So the system will not work. Actually, that's what happens. If a system is designed to correct a maximum of two-bit errors, if there are 3-bit errors, does not mean to correct the 2. It means it would correct the errors. Yeah? Am I making sense? If
Yes.
a system to correct 2 bits. Doesn't mean when 3 bits come, it will correct 2 and leave 1. No, it means it will not correct the bits. And even when we talk obviously the Hamming code means it will correct single bit errors. But it's because we're also making assumption that in most systems, 99.99%. So I think sometimes we go to the 5 nines, 9.9999999, yeah, percent will be single bit errors. That means there are still some things that will not be corrected. Yeah, it will tell you you are not corrected, but it may have detected. Because remember, the error detecting capability is normally higher than the error correcting capability. So if it detects, it won't accept the information. It will drop the information. Yeah, but at least you'll be safe. You know that information is, you won't accept the information. So that's what would have happened with the Voyager. The information they were getting, it was not correcting. But at least they knew it is garbage. Yeah, they knew what they are getting is not what was sent, because it means it was just dropping packets. Yeah. I hope I answered your question. Okay, that was the first concern. Second concern.
Yes, yes, thank you. The second one was on a separate article that I read that
Yeah.
in 2003 in Belgium, they were kind of having some form of electronic voting, and I don't know, a cosmic ray hit the computer and a certain candidate got more votes that surpassed the registered voters, and it kind of showed that there was something happening. And after investigation, they found that a single bit had flipped, and the candidate had received 4096 extra votes. So what kind of mechanisms would you think maybe that were later incorporated in such a system to make sure such an upset doesn't happen? And what is the possibility of having a cosmic ray actually making a system a bit to flip?
Oh, okay. That's an interesting one. You see, the moment you say cosmic ray, it means you are getting unexpected errors. So probably there are no mechanism for checking such an error. You know, when you design a system, there are those errors which you can expect. And so again, it will come to the same thing. Your inability, if it is error checking. But of course, we are not, we are saying, we are removing the possibility of a human error. So we're just thinking that maybe the system failed. And it failed, what do you call it? It failed unsafely. Yeah, it was not fail safe. The system failed, but its failure, I don't know that's the only thing I can attribute error correction capabilities. But I'm trying to think one bit changing can actually change a figure to be, it's true, if one bit change, depending on where that bit has changed, it can actually mean increasing the figure to a very large figure. Yeah. If one bit change, just even simple math, if you have got, let's say, let's say this is that in decimal. If you convert this to decimal, depending on which bit change, the value can actually go very high. So if you are sending information, if you're sending information in binary and one bit changes on the way, in fact, I can see how that would happen. For example, you want to send a certain figure in binary to say this person you want to transmit because you are transmitting electronically that this person gets the number of votes. If a bit change and there is no error correction mechanism, then it should mean actually you will end up sending the wrong figure. Yeah, that one just means it's a system where they do not expect errors to happen. And then the cosmic they happened, therefore it could still actually be connected to the error correcting capability of the equipment, or rather not being provided because there are systems whereby we don't even provide uh, where we don't expect errors, so we don't provide any error correcting capability because error correcting capability means redundancy. Yeah, and that redundancy means more bandwidth. That's the only way I can think about it. You are not concerned?
Yes, thank you. And my last concern, you see in our telecoms lab that we've been going to since third year, when we look at the top shelves, they usually Cisco equipment that were, I think, donated, and there are some switches, routers, and some basically other networking equipment that unfortunately for our 5 years, we've never quite had the time or let's say usually the time to access them, mostly because of the requirement, our academic requirement, in as much as the technologists are usually open to us accessing them. So I don't know if there's something that can be improved maybe on our end or on the curriculum end to make use of those equipment because they're just there, I'd say, for lack of a better term, rotting.
Oh yeah. That might be tricky with your current syllabus, because that configuring routers, I think the closest you come is what we are doing now. But again, we are 4 weeks, so we and that would mean also tailoring the lab so that you can do device configuration. I think I'm not in your syllabus. I don't know. You can correct me. You don't do computer networks anywhere. You do introduction to computers.
Yes,
Am I right?
yes.
Yeah, you don't do computers. So normally, if you do computers or units that have got networking, would be computer networks, data communication, network design. There's normally a course like that one at the university level. So if you are not doing those, that might be now unless you do it at the introductory level, which I don't know whether you do computer introduction to computers in your first year. It may not go that deep that you can be able to configure the devices. Yeah, that might be a ticket. It could mean working on your syllabus so that you have more computing units, especially for networking. Yeah, I wish I could be able to do it in this unit, but again, in this unit, we have to liaise with the lab, and then it means we have to do network devices. I think we won't have time to do network devices in detail, but I think from if you go through the OSI model with that document I've sent you there, because to do that we need to do specific and apart from the OSI model, we need to go a bit deep into something called routing. Yeah. So routing itself is another topic where you look at all the various protocols, including these ones which are used by Cisco. Yeah. So that one, my advice is probably it might be important once you leave, you can try to once you leave university, before you get a job, you can try to do some Cisco courses. They are being offered in various organizations. In fact, I believe Cisco have partnership also with Nairobi University, so they could also be offering those courses internally, but not part of your curriculum. Yeah. So your concern is valid, because I think, especially when you're doing light current, it is important at least you are able to work in the networking area. You have enough knowledge in the networking area. Did I address your concern, or did I say something to your concern?
Yes, thank you. Maybe I would ask if you're in a position to maybe give suggestions to the department, so that maybe for third year, for example, to have some form of electives for the students, whether choose between machines and maybe the networking. I don't know. Maybe it would help.
Or you specialize a bit earlier? You are
Yes.
specializing now in year 4.
Yeah. No, 5.
I think you have some telecoms units in year 4.
Yes.
Yeah, so it looks like you start specializing at year 4. So probably you proposed that probably you start specializing earlier. Or maybe in 4th year itself. Yeah. But I did hear, I think when I came in 2020. I think you are working on the curriculum. I don't know how far they have gone. Maybe that should be one of the units. I can mention to the chairman and see what can be done. Whether that will be possible. I think I would recommend that at least you do computer networks as a unit.
Yes, thank you.
Okay, welcome. So I thought we'll be able to touch on introduction to computers. We have about 15 minutes. So I think I'll send you this document. Why actually I had not sent you, because I've been making it a bit basic. But maybe I'm thinking that maybe we need to, because it's a very basic summary of a computer network course, because most of the things which are mentioned in this unit, now you end up going deep into them. Yeah. So I think we will look at this next week, and then we'll go to the OSI model. I expect to do around 4 topics in computer networking, because we have only 3 weeks. If we had more weeks, I could have. But actually, it's not possible to cover the whole computer networks at the undergraduate level in 3 weeks. So we try to cover what we think is enough to be able to design a simple network, probably, and maybe even configure simple network devices. And actually, when it comes to configuring the Cisco routers, it's normally at the high end of configuration, because they use very proprietary software for configuration. They call it the iOS. Yeah. They call it Cisco. I think they call it also iOS. You see, there is iOS for the phone. I mean, for the iPhones. I think they also call it iOS. The software they use, which is very specific to Cisco, very proprietary. So that's normally the next level of configuring. But configuring basic wireless routers, the ones Nini is normally a good start before you get to configuring the Cisco. And you see, with Cisco nowadays, I can see you can configure in a GUI. Most of Cisco configuration is done in the command line. So you need to be quite familiar with the Cisco commands. Yeah. Which sometimes, even with a basic understanding of networking, you still need to be exposed to Cisco routers and learn their Cisco commands before you can be able to configure them. So I hope everybody has sent the registration to the chat, because I intend to stop there until next week. So we are dealing with error correcting codes, and what you're going to do from now is mainly selected topics in computer networking, so that we are able to design and analyze a network. Have a good day. See you next week.